Ladies and gentlemen, let's continue with chapter 4 out of the textbook of Cengel and Ghajar. It's the last part that we are going to do in this chapter, and the chapter consists of 4 parts: the lumped part, the lumped system approach, which is a very simple approach, but with lots of limitations. Then the second part was the transient heat conduction in large plane walls, long cylinders and spheres. Then with the previous lecture, we've looked at transient heat conduction in semi-infinite solids, and today we're going to do the last part, which is paragraph 4.4, multidimensional systems. Now, with the multidimensional systems, what we are doing now is we are going to extend our previous solutions, which were one-dimensional in nature and which was only valid for certain geometries, specifically the 3 geometries of the large plane wall, for the long cylinder and the sphere. Those 3 were all one-dimensional solutions. And because it was only one-dimensional, it means that the plane wall that should be considered should be very long, so that the other surfaces are negligible in terms of the total surface area, and the same with the cylinder, that the top and the bottom is negligible in comparison with the rest. With the sphere, it doesn't matter. So what is being done in this part of the textbook is a very elegant solution by making use of these solutions and extend the solutions to a 2-dimensional or 3-dimensional solution, and to make that possible, use is being made of the principle of superposition, in which you use the product solution. And the result of that is that we now can have 2-dimensional and 3-dimensional problems, heat transfer problems, with other geometries also. Not only the 3 geometries that we've considered in paragraph 4.2. A good example is now taking the example of a long cylinder. Okay, there it is, like that, schematically. Okay. And we've said that is the coordinate system R, and that is the radius R0. So the solution in your textbook is specifically for this. The heat transfer rate is in 1 dimension only, which is in the R direction, all the way around. Okay. And taking the solution for a large plane wall, one like that. Okay. And here's our coordinate system. Okay, and the coordinate system is x in that direction, and that distance there was equal to 2L. 2L in terms of the width. Now, with the principle of superposition, what we now can do is we can take this solution and that solution and multiply it with each other. And that gives us now another geometry. Let me see if I can get it. Oh, no. Unfortunately, these are not on. Let me see if I can get them to be on. Okay, so unfortunately, it will not be possible for me to show it to you with data projectors, but you'll be able to see it on the laptop later. But the result of this is, and my sketch is never so good, is that with the principle of superposition, we are now going to have this plane wall like that. So those two cross each other. If you can use a little bit of your imagination, R0 and there's 2L. Okay. And the result of that is what is called a short cylinder. So the short cylinder would typically be that, like that. So the resulting geometry for which we can get a solution now looks like that. And in terms of the mathematics, it's very simple. It just means that the temperature is now a function of R, X, and T minus T infinite divided by Ti minus T infinite for a short cylinder, and that is equal to the temperature xt minus T infinite divided by Ti minus T infinite for the large plane wall multiplied by the solution for the cylinder. And in table 4.5, for those of you who've got your textbooks here, something like 9 solutions are given. Okay, I'm going to try to take you through those. Okay. So there's typically an example of, just as I've showed now, the cylinder and the plane wall. And then there's another example of 2 plane walls. And that would now form a cubic type of geometry. And in table 4.5, there are then various geometries for which the solutions are available. Maybe I can still get this on before the end of the lecture. Let me hope so. Yeah, they're coming on now. So if you can be a little bit more patient, then I will show it to you on the data projectors. Okay. Now, if you look at table 4.5, obviously, if you now would like to look at the dead body that we've considered previously, the assumption was that there was no heat transfer through those 2 areas there, because our assumption was that it's a very long cylinder. What you now can do is you can redo the problem, but using the solution, and you can get a more accurate answer for the dead body by now also taking into consideration the heat transfer rate through the head and through the feet. The most important thing for these solutions is to look at the coordinate system. The coordinate system is really the secret, the successful solution of many problems. And you don't have to learn it, they are all there. In the sketches, you can just look at them. Let me see if I can get that thing going now. I don't think those images are from my laptop. It's from a computer inside here. Let's see if I can change it. Now, unfortunately, I'm not successful with getting the data projector working. So let's look at an example. Okay, the example is going to be a piece of brass, cylindrical, K value of 110 watts per meter Kelvin. Alpha is equal to 33.9 multiplied by 10 to the minus 6 square meters per second. The initial temperature is 120 degrees Celsius. The density is equal to 8580 kilograms per cubic meters. And the Cp value is equal to 380 joules per kilogram Kelvin. The environment temperature is 25. The heat transfer coefficient of the environment is 60 watts per square meter degrees Celsius. And the dimensions of the cylinder is a diameter of 100 and a height of 120 millimeters. And the question is to determine the temperature. I'm going to call this temperature at point Z. There's point Z there. The temperature at point Z at T equal 15 minutes. So a brass cylinder, initially at 120 degrees Celsius. Those are the properties. At T equals 0, it is exposed to an environment at temperature 25, heat transfer coefficient of 60, and now it's cooling down. And we want to know what is the temperature at that point there. Because of symmetry, it would also mean that the temperature at point Z will be the temperature everywhere on that circular radius. Okay, at least one is working, so let me just take you through the slides. Okay. So there's the two geometries, and there you can see the intersect between the two. The sketch is much better than mine on the board. Okay. And then for the case, there it is on the other slide also. For the two plane walls, there you see the geometry that can be generated. And this is now part of the table. This is an enlarged part, and there you can see some of the different geometries. So this first one is the long cylinder, as it was, and this one is now one where it's very long in that direction. And if you look at the cursor, it will be insulated there because there's no heat transfer rate through there. However, there's a heat transfer rate through the surface there. Oh goodness. Yeah, it's coming back, right? Okay. So the heat transfer rate is through that surface there. And now the one we are considering, long cylinder, product with a plain wall. And there's a solution. Okay. It is just written in a non-dimensional format, and take note of the R and the X, and take note of where the coordinate system is being placed. It is exactly in the center. If you would go and do the problem and you would put your coordinate system there, then it's going to be incorrect. So it's very important that you put your coordinate system at the right place. And there you can see other types of geometries. 12 of them in your textbook. There are many more available in literature, but these 12 are some of the most important ones. Okay, so as I've said, the most important thing here is to go and put in your coordinate system and put it in at the right place. Okay, so if you do it correctly, then point Z would be the case where R is equal to 0.050 meters, 50 millimeters, and point X would be equal to 60 millimeters. You agree? So that would be where the radius is 50 millimeters, because the diameter is 100. So that's on that radius, and that would be where this distance X is 120. So sorry, that is the distance X, and that is R in the coordinate system. Are you happy with that? Okay. Then, for this specific geometry, it would then give us the solution, the non-dimensionalized solution of X, R, and T is now equal to the solution from the cylinder, which is a function of RT, multiplied by the solution for the plane wall, which is a function of X and T. So the one-dimensional solution, in this case as a function of R, and in that case as a function of X, now becomes a function of two variables, X and R, and not only of T anymore. Okay. What does that mean again? It means that it is just a non-dimensionalized temperature for a cylinder, and that is equal to the solution of A1E to the minus lambda 1 square multiplied by tau J0 lambda 1 multiplied by R divided by R0. And for the wall, it would be equal to something very similar, A1E to the minus lambda 1 square tau, and the cos of lambda 1 multiplied by X divided by L. And this is equation 423 in your textbook, and that is equation 424. See if I can show that to you quickly. There you go. The solution for the plane wall and for the cylinder, assuming only one term. So assume that tau is larger than 0.2, and that we only have to use the first term approach. Okay, so how do we solve a problem like this? Well, we're first going to look at the solution for the wall, and then the solution for the cylinder, and we're just going to multiply it with each other. So let's do, if you can divide your page maybe in two. If you want to, you can do the wall on the left-hand side and the cylinder on the right-hand side. Okay. So for the wall, the Biot number is equal to the heat transfer coefficient multiplied by L divided by K. Where do I get it? In the fine print. In the fine print underneath that table, it gives you the Biot number is equal to HL divided by K, not LC, using the lump system dimension. Okay, now with that Biot number, equal to the heat transfer coefficient. What is the heat transfer coefficient? It's equal to 60 multiplied by the length, and the length is 60 millimeters. Okay, 60 millimeters divided by the thermal conductivity, and the thermal conductivity is 110, and that will give us a Biot number of 0.03273. So the Biot number is small. Okay. Tau is equal to alpha T divided by L squared. Alpha has been given as 33.9 multiplied by 10 to the minus 6. The time T is, we want the solution after 15 minutes. So it's 15 multiplied by 60 divided by the length squared. The length would be equal to 0.06 square like that. And that gives a value of 8.48. Non-dimensionalized time of 8.48, and it is larger than 0.2. So the one-term approximation would be valid. So with a Biot number given, we can go to table 4.2, and we can get lambda 1 is equal to 0.1799, and A1 is equal to 1.005. Let me see if I can show you quickly. There it is, for the plane wall, for a Biot number of 0.032, somewhere there, and there you should be able to see that the values are approximately correct. Okay. Okay. So that is for the plane wall. Let's look at the cylinder. For the cylinder, take note, the Biot number is equal to H multiplied by R0 divided by K. Where do I get it? In the fine print underneath the table. The heat transfer coefficient is equal to 60. The diameter is 50 moles. The thermal conductivity is 110, and it gives a Biot number of equal to 0.02727. Okay. The non-dimensionalized time also is equal to alpha T, but now divided by R0 squared. Okay. Okay, those values stay the same as previously. The radius now becomes 50 moles. Previously it was 60 L, now we use R. So the non-dimensionalized time is still larger than 0.2, which is great. And then again from table 4.2, we can get lambda 1 as equal to 0.2328, and A1 is equal to 1.007. Just look in the table quickly, if you can see that. A Biot number of 0.02, approximately there. But now we have to look for the values of the cylinder. So we have to look at those values, not those ones, the one for the cylinder here. Okay. Right, so coming back to the solution, you can see that what we've got now is we've got the A1 values, we've got the lambda values. But for this case, we have to get the J0 values. Here it's going to be the cos of that. So we need to get the J0, value of lambda multiplied by r divided by r0. Okay, and that is then equal to J0 lambda we have determined now is equal to 0.2328, and we want the solution where the radius is equal to 50 mils. That is where we want the solution. But however, the radius R0 is 50, so that ratio is equal to 1, which means that we actually want the J0 value at 0.2328, and this part is known as eta. So eta is equal to 0.2328, eta, and in table 4.3, here it is, here are the different values for eta. So at a value of 0.23, we can get the J0 value from table 4.3. So table 4.3, we can go and get it, and the result is that J0 is equal to 0.9865. For those of you who can't see it, J0 is equal to 0.9865. 0.9865. Okay, so if we still continue, if I still continue here on the wall side, so let's go and calculate that value there. So let's call that equation 2 and that equation 1. So making use of equation 2, the non-dimensionalized temperature, okay, wait, you can't see properly there, let me rather do it here. Okay, so equation 2, the non-dimensionalized temperature of the wall is equal to A1e to the minus lambda 1 square tau multiplied by the cos of lambda 1 multiplied by x divided by L. And that is equal to A1, here's the value, 1.005, e to the minus lambda is equal to, let me make some more room, (1.005) e to the minus 0.1799 square multiplied by the cos of lambda 1, which is 0.1799, multiplied by x, and x is equal to 60 millimeters, divided by L, which is 60 millimeters. And if we solve that, it is equal to 0.7638, the non-dimensionalized temperature. Do you follow? This question. Where did tau disappear to? Sorry, yeah. It's a lack of space. 8.48, or you must just, it's a little bit small there. There it is, 8.48, thanks. Okay. Okay, so that's the left-hand side. Let's do the right-hand side, the one for the cylinder. So now we want to look at equation 1. Equation 1 for the cylinder. Phi for the cylinder is equal to A1e to the minus lambda 1 square multiplied by tau. J0 multiplied by lambda 1 multiplied by r divided by r0. Okay, A1 is equal to 1.007 multiplied by e to the minus 0.2328 square multiplied by tau, which is 12.2, multiplied by J0 in that term, and we've already calculated it as 0.9865. And that gives us a non-dimensionalized temperature of 0.5128. Okay, so we've completed the non-dimensionalized temperatures for the long plane wall and for the cylinder, and now we have to do the product solution. And the product solution says that the solution is equal to just that of the cylinder multiplied by the wall. Okay, so from the non-dimensionalized temperature at x, r, and t, which is equal to the non-dimensionalized temperature of the cylinder multiplied by that of the wall. What is this non-dimensionalized temperature? Well, it is the temperature at r, x, and t minus T infinite divided by T infinite, T initial minus T infinite is equal to the non-dimensionalized temperature of the cylinder, which is equal to 0.5128 multiplied by the non-dimensionalized temperature of the wall, 0.7638. Now we can do the substitution of the other values also. This temperature is the temperature at point Z that we are interested in, minus the environment temperature is 25. The initial temperature is 120, minus again the environment temperature, which is 25. And that all is equal to, if you do the calculation, equal to 0.266. From which you can solve that the temperature at point Z is 50.3 degrees Celsius. 50.3 degrees Celsius. Okay. Are you all happy with that? Do you understand the principle? Okay, now let's suppose I've also asked you, I actually want the temperature at this point here. The temperature T at the top, in the center there. How will you change the problem? So we also want the temperature there. Okay. So all you need to do now is you need to redo the problem, but now for R equal to 0, because it's on the center line, with X equal to 0.060. You agree? Okay. Or the case for the temperature T0. And where's T0? T0 is exactly in the center. This point there. Temperature T0. If you want the temperature T0, then R is equal to 0 and X is also equal to 0. We don't have time to go through all the details, but again, if you look at this, the Biot number is going to stay the same, and that one is going to stay the same. So the lambda 1 and the A1s are going to stay the same. It is just where you have to put in the x, depending on if it's 60 or if it's 0. And that is about it. And there also R and R0.
Sorry, I just want to ask, the JO value will also then change?
Yes. So the JO value would also change because the JO value is R divided by R0. R divided by R0. Okay, so R becomes 0 now. It means it is the JO value of 0. And I think that's equal to 1. Okay. Now, if you do this problem, then you're going to find that the temperature at the center is 62.3 degrees Celsius. Okay. So this is what the lump system approach cannot do. The lump system approach is going to give you one temperature, but it cannot differentiate between different temperatures in the body. Again, if you go and redo the problem now for us a lump system. Okay, but before we do that, any questions on this approach? Yes, there's two.
So the calculation there was previously 0.5 times 0.7. It's not equal to 0.6.
Do you mean that too?
No, it's to the left. The final answer is not right there.
Is that one?
Yeah,
Okay.
0.39.
Okay, 0.39, thank you. And if you want to check that temperature, did anybody work it out? 62.05. Okay. Okay. So most probably that temperature is also then incorrect. So just go and check it. Can I redo it? If we do the lump system approach, with the lump system approach, this is now where things are different. We work out the characteristic length always as the volume divided by the surface area. The volume by the surface area, and if you go and calculate it, it is equal to 0.01765. If you use that to calculate the Biot number, now, based on this characteristic length of calculating it like that, then the Biot number is equal to 0.009626. The B value, which contains the heat transfer coefficient, multiplied by the surface area divided by rho, the volume, and Cp. You can go and calculate that, and then you can solve the temperature as function of time, T minus 25, 120 minus 25 is e to the minus bt. The T is 15 minutes multiplied by 60. You can go and calculate this temperature, and I've calculated it as 62.16 degrees Celsius. Okay. So the lump system approach, this temperature and that temperature now are very close to each other. But remember, the lump system approach is valid for Biot numbers smaller than 0.1. In this case, it is. It is for high thermal conductivities. In this case, brass has a high thermal conductivity. Characteristic length, in this case, if you go and pick up a piece of brass like that, you will feel it is actually quite big. So in terms of the length, it's not that small. And you can get actually quite a good temperature. However, with the lump system approach, the temperature at point R is going to be equal to the temperature at point 0 is going to be equal to the temperature at point T. Cannot differentiate. And that is the advantage of using the other methods. So to summarize, if you look at all the problems that you can solve, where you would like to solve the temperature as a function of time, then the lump system approach is a small number of problems or small number of cases where it is valid and it is actually the right approach to use. Any questions, ladies and gentlemen? If not, thanks, Tamron, you can stop.